Okay, in these three problems, we're going to take a look at the central limit theorem. So for each of these, these problems come in sets of two. For the first part, we're going to calculate the probability for one randomly selected data value using the regular z-score formula. That part should be nothing new. And then we're going to take a look at the same scenario but applied to a sample rather than just an individual. So in that case, we'll be using the central limit theorem. Okay, so the first part should be familiar. Heights of American adult women are normally distributed with a mean of 63.6 and a standard deviation of 2.5. Find the probability that the mean height of one randomly selected woman is greater than 5.5. I'm sorry, 5 foot 5 inches. When I first started doing this problem, I just went ahead and automatically did the calculation in my mind that 5 foot 5 inches is 65 inches, and students were lost at the get-go. So I kind of added this in here. 5 foot 5 inches, 5 feet, each foot has 12 inches, plus 5 more would be 65. So isn't my neatest work, but I needed to squeeze it in there. Okay, so that's how I got the 65. I'm going to take away the mean, divide by the standard deviation, and I get a z-score of 0.56. So when I look at the normal distribution, I find that a z-score of 0.56 is associated with a probability of 0.7123, but we need to remember that's the area to the left because the probability on that chart is always to the left. We are looking at greater than 5 foot 5 inches, so we need to use the complement rule and take that away from 100 or 1, and we find our probability to the right of that data value of 65. That data of 65 inches would be at this borderline right here. I didn't write it in there, I ran out of space, would be 0.2877. So, you know, I guess it's a total of 1.4 inches taller than the average. You're going to get any taller than that would be, 28% is not that far off. Okay, find the probability that the mean height of 12 randomly selected women is greater than 5 foot 5 inches or greater than 65 inches. So again, we plug in the same scenario in our numerator, but our denominator has changed. We are going to have to make an adjustment because this is from a small sample. And so we're going to take our standard deviation 2.5, divide by the square root of 12. So when we do that, I didn't write it here, but I guess that denominator would now have been 0.722, and when we divide that out, we get a much higher z-score. We go to the normal distribution to find the z-score that is associated with 1.94, and holy cow, we get a really high score of 0.9738. We take that away from 1 and we're left with 0.0262. So when we look at a sample, our probability of getting a sample of women at that height, a sample of women whose average height is at that height, is much smaller. It's just very unlikely that we would get that. I want to go ahead and show you this in StatCrunch. Okay, so in StatCrunch, we're going to go to calculators, down to normal. Stat calculators down to normal. I need to put in my height of, I believe it was 63.6. And we've got a standard deviation of 2.5. And this is the first part, and we are looking for 65. And remember, we have to change the sign because we're looking for the probability of getting a height greater than that. So we end up, that was the first part of our problem. We got 0.2877, and we can see that, a fair percentage of women will be taller than that. So the chances of getting one taller than the 63.6 is a little more than a quarter of the population there. But now when we're going to use a sample, getting a sample of 12 women who have that height, we have to recalculate our standard deviation. So when we take that 1.4 difference, I got that 1.4 by taking 65 minus the 63.6 and dividing by 2.5, divide by the square root of 12 because our sample size was 12. I get a new standard deviation of 0.722. So I need to adjust the standard deviation in StatCrunch. and I can see that I get a much smaller outcome, 2.62 according to StatCrunch here. So the chances of getting a whole group of 12 women whose average height is 65 or greater is much, much more slim. You must be hanging out at a school for models or something because they're unusually tall there. Okay, so we're going to put that aside and continue on. Okay, this problem I kind of like because it's true. This actually was found. The elevator at the San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds or 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. So in other words, we took the 4,000 divided by 27 to get this average weight of 148. Let's assume the worst case scenario in which the elevator is filled with 27 adult males, and that adult males have a weight that are normally distributed with a mean of 189 and a standard deviation of 39. Find the probability that one randomly selected adult male has a weight that is greater than 148. When we go ahead and do this one, it's a regular process, very similar to the one above. Plug in the information into our z-score formula. We get a z-score of negative 1.05. The probability that is associated with that z-score is 0.1469. But remember, that's to the left. That's that blank spot right here. We don't want this. We're looking for the probability of getting a height that is greater than 148. So we're going to have to take this away from 1, and that's where we get the 0.8531. So we have an 85% chance of getting a male, randomly selected male, whose weight is greater than 148. And that kind of makes sense. Okay, now we want to find the probability that a sample of 27 randomly selected adult males has a mean that is greater than 148. What are the chances of getting a sample of 27 males greater than that? I'm thinking it's got to be really huge, because if this was 85% chance of getting one male, I think getting a random sample where the average was greater than 148 is going to be almost a sure thing. So we plug in our formula. Remember, we have to adjust our standard deviation down here. So in that case, I didn't write it on here, but in that case, our new standard deviation would be 7.505. We get a severely small z-score. Our z-score chart doesn't even provide that for us because it is so small. So when we plug that in, probability that is associated with a z-score of negative 5.46, we just identify that it's less than 0.001, in other words, less than 1/10,000th. So this was to the left. So the chance when we take that away, when we take that small probability away, we end up getting a much bigger, so we almost have a sure chance, a 99.99% chance of getting a group of males who are, the average weight is greater than 148. So again, I'm going to show you how to do that in StatCrunch. So we're going to go to Stats, Calculators, down to Normal. I keep losing my paper on you. Okay, for my mean, I'm going to put in 189. Average weight of males was 189 with a standard deviation of 39. This is, I'm calculating for 1 at this point, so we can see the difference. Okay, and we're going to compare the chances of getting one male that is greater, and I need to change that. And we automatically came up with our 85. So we've got a pretty good chance that we're going to randomly select one male who's greater than 148. But when we're looking at a group of, I think we had 27, we would take that 39 that we had in here, divide by the square root of 27, and we would end up with a new standard deviation of 7. I'm going to put 505 in here and compute that. And holy cow, we've got almost a surefire. The whole thing is shaded in. It's such an extreme difference. When we look at the probability, 99.99, on and on. So a very great chance that we're going to get a group of 27 males whose average weight is greater than 148. So in my mind, I'm thinking maybe they should change the placard on that elevator. To this day, I get on an elevator and I check that out now. Okay, the next one, the population of human body temperatures has a mean of 98.6 with a standard deviation of 62, find the probability that a randomly selected person has a body temperature, I should have written in here, less than 97.6, so please make that adjustment if you don't have it adjusted on your paper already. It wouldn't make sense if I said equal, but less than. Okay, so we're plugging in our normal information into the z-score formula. We get a z-score of negative 1.13. When we look at our table to identify the z-score that equates to that, we end up with a z-score of the probability that a rate equates to that z-score, we end up with a probability of almost 13%. So 13%, according to the 98.6 with a standard deviation of 62, we could also assume that 13% of the population has a standard body temperature less than this 97.9, which that's a fair distance away. It's more than the 62, one standard deviation away. So that would be just looking at one person. Now we're going to look at a sample of 96 randomly selected persons and find the probability of getting a mean that is less than 97.9. So let's see how often that would happen, or how likely that would be to happen. We plug in our information. Again, we have to adjust our standard deviation because we're looking at a sample of 96. The average of all 96 people, the average of their body temperature is 97.9. That's a pretty big group to have that much of a drop in body temperature. We find that we have a z-score, again, off the charts, negative 11.06. So generally what you write is that the probability that is associated with that small of a z-score is less than 0.0001. Extremely low probability. In fact, I kind of bubbled in something here so you can see that I didn't ignore it, but that probably doesn't even do it justice. It's way out here. I'm going to go ahead and do this again on StatCrunch. So stat, calculators, down to normal. We've got our standard default again, but I need to put in our mean. The advertised mean is 98.6. Standard deviation is 0.62. We're checking out the likelihood of 97.9. I believe that's what I have here. Okay, and looking at just one individual, yeah, about 13% we could expect would fall below that 97.9 when we're looking at one individual. But when we're looking at a group of 96, I believe it was, I would have to take my 0.62 and divide by the square root of 96, which you need to do this with your calculator on all of these, would be 0.063. When I calculate that, it looks like I have a blank chart because it is way down here. It doesn't even show up and register on the StatCrunch chart. It is that low of a possibility. And we look at the probability here. It says E negative 29. That's exponential notation, meaning this decimal is moves to the left 29 places. Really, really minutely small chance of getting a group that size. So that actually is a true scenario here. When you're looking at that kind of an outcome, you would figure either your thermometer is faulty, or the data is wrong, or perhaps your hypothesis that the true body temperature is not right. It's not equal to 98.6. And so I just wanted to point out that many doctors had reported over the time frame over the last century. Doctors' offices often report that body temperatures, patient body temperatures are often in the high 97 or low 98 range. And so the University of Maryland recently initiated a nationwide testing and got these same results that we got here, and it's now speculated that the true average body temperature is actually closer to 98.2, not 98.6. So it's speculated that that 98.6 guideline for normal body temperature needs to be updated. It was probably established back around the turn of the last century. Either our measuring tools have gotten much better, or as a race, perhaps our body temperature is just dropping. Who knows? Global warming, body temperature dropping? It could happen, right?